We are in the week 7 problem solving session of the NPTEL course, Control and Tuning Methods in Switch Mode Power Converters. And week 7 is about small signal design and tuning of PWM voltage mode control. I am Teja Golla, a 5th year research scholar working under Dr. Sandar Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Can you see my screen?
Yes, sir, it is visible.
So have you gone through this week's lectures?
Yes, sir, yes. I
Okay,
have gone through it.
Okay, you have understood how to design the controller, or do you have any confusion in that? So accordingly, I will spend time on the topics. So how confident are you in understanding the controller design and of pole zero cancellation?
That basic idea is somewhat clear
Okay,
about pole zero cancellation.
but not so confident.
If you can quickly go review
Okay,
it. In yesterday's session, I think boost converter related
yes, yes,
design
yes.
was
Today I'll discuss
shown.
regarding the buck converter design, buck converter based design. So first I'll start with the small signal closed loop block diagram. Okay. So in our previous class, if you remember, we have discussed about this uh, implementation using the blocks. Now what we are going to discuss is now we'll see how this finishes our overall closed loop block diagram. So in the previous week, whatever we have discussed about the small signal transfer functions. So now in these small signal transfer functions, we need to add a few more blocks. Like one is the sensor. So output voltage sensor, and then main thing is error generator, because there is a reference and then we have to subtract the output from the reference, right? So we have to also draw the block of error generator, and then we'll also be needing controller because controller is missing, and then we'll also need something called modulator. Okay, so now we are going to add these four in the original block diagram, and let us see how does it look like the overall things. So first of all, I input usually in practical implementation, input current is never like an input to the system, because in our system, voltage is the input, right? Current is usually not the input. So what we do is we'll not use this part. So why? Because I input is never the input to our circuit. I input is drawn from a voltage source, because in all the circuits, voltage source is an input and current source is not an input. But theoretically, we can get the V inputter from I inputter, but practically, IN is actually being drawn from the input voltage. So we usually don't show this in the representation. So I'm going to erase this. Okay. So now I'll just quickly interchange this. So for the ease of, so V in part I'll put here, and then GVD, I'll swap the places. So I am going to write this as V in part, and then this is as GVG of S. This is GVD of S, and then this is D part. So now we are basically discussing about the voltage mode control, right? So if you know, how are we generating the duty ratio? Can anyone tell me how we have generated the duty ratio? Like duty ratio, how are we generating from the control voltage?
We will compare a reference voltage with a sawtooth voltage,
Yes,
and the
yes,
error signal is passed to the controller. The
yes. Very
controller
good.
output will be duty.
Yeah, continue, continue.
The controller output will be the duty ratio signal.
Yes. So as you said, we have a sawtooth, and then it is compared with the control voltage, right? So this is our say Vcon, which is the output of the controller. And then we have discussed that this ramp voltage can have a magnitude of Vm. So now my duty ratio D will be nothing but Vcon by Vm. If 1 by Vm is Fm, then I'll have Fm into Vcon. So basically I can further write it as if I have part of everything, Fm is constant, so Fm is Fm into Vcon part of it. So from this, what we can do is, so if my D part up is Fm into Vcon, so here Fm is the modulator gain. So you have to understand all these terms and which are very important. So this modulator gain is coming because of the ramp voltage. If the ramp voltage is 1, modulator gain is 1, so D part up will become Vcon part up. But if the ramp voltage is not 1, say it is more than 1 or less than 1, then this voltage will result in a non-unity modulator gain Fm, which will also impact the loop transfer function. So that's why modulator gain is very important, because according to the gain, the loop transfer function can vary. So we'll check the loop transfer function of a buck converter today, because yesterday Calvin has discussed about the boost. So we'll dive into the loop transfer function, all the poles, zeros, how we are going to design, and why we are following these guidelines, by PID, by type 3, all these details we are going to discuss. So if you have any doubts, you can stop me. So now I have D butter. So now what I'm going to do is, there is a FM. So now if this is the block, now the input of this will be recon pattern, right? Everyone agree? Hello,
Yes,
is
sir.
this clear? Yeah. So now, how, from where beacon is coming? So beacon is a control voltage, which means the output of a controller. So if I assume the controller to be GC of S, then the output of the controller is beacon pattern, and the input of the controller is error voltage. So which is my VE pattern. And what is VE pattern? VE pattern is nothing but V reference minus V naught pattern. So this is my V reference pattern, and this is my V naught pattern of us. V naught pattern. Sometimes we can also have a gain, because we need sensing, right? So output voltage, if it is very high, then you might have to step it down. So we'll have a sensing gain. Also, we can do filtering so that noise can be removed. All signal processing can be there, and combining all this, we can consider a gain of K sense. Okay. So now this is our overall block diagram. Now this is a loop, right? So now this is a loop. Now this is a loop, and this is called K loop of S, which is the loop transfer function. If we do the product of all the blocks, which is GC into FM into GVD into K sense. But usually K sense will be there. In the lecture, sir has not considered K sense, so I am also going to consider it to be one. for the time being, or you can consider there is no cases and we can proceed further. But like in practical implementation, there can be cases. So you have to consider cases also into the picture and then design accordingly. So there will be one additional gain term in all the calculations that sir has shown. So this is the overall block diagram. If we are discussing about the overall loop, so this is the small signal block diagram, which consists of all the blocks. In the previous week, we have discussed only the small signal transfer functions. Now we have also discussed for voltage mode control. What are the things that are going to be added in addition to the original block diagram, and what are the individual terms, which is also very important. Is this clear until this point?
Yes, sir, it is clear.
Okay. So if others have any doubts, you can ask, and else we'll proceed further. So if you don't have any further queries, I will just directly write the K loop of S expression, which will be using further to design the controller. K loop of S is GC of S into FM into GVD. So now we are going to design the controller so that the loop transfer function will have whatever is our desired bandwidth as well as desired phase margin. So these are our requirements. So this is the requirement that we have. So now meeting these requirements, we need to design the controller so that we can use that controller as a part of our system to drive the plant so that we can meet the desired specifications or requirements. So this is our overall objective in this week. Whether the converter may be buck or boost, we are basically dealing with the transfer function. So if we are given a transfer function, how are we going to design it, and what are the guidelines that we are going to follow, and what are the different methods that are available. So this will be our discussion. But before we design the PID controller, I want to highlight what is ideal and what is practical PID controller, and why do we need practical PID controller. So can anyone tell me the difference between ideal and practical PID controller, and why do we need to consider practical PID and not ideal? Okay, can anyone tell me the transfer function of a PID controller?
KP plus KI by S plus KD into S.
Yes, very good. So this is Kp plus Ki by S plus Kd into S. So is this proper or improper? Can anyone tell? Do you know what is proper transfer function, improper transfer function, strictly proper transfer function?
Numerator should be, the power of S should be less than that of denominator.
Yes. So if so there are say the degree of the numerator, say degree of numerator, I am calling it as n numerator, and then degree of denominator, I am calling it as n denominator. So now we have three cases. As you know, when there are two numbers, we'll get three cases. First is n numerator is less than n denominator, and n numerator is equal to n denominator, and n numerator is greater than n denominator. So if the numerator degree is less than denominator, which transfer function is that? Okay.
Nu-
So yes.
Numerator degree less than denominator is strictly proper.
Yes, very good. So this is strictly proper. And the other cases?
Improper.
Okay. Which one is improper? Second one or third one?
Second one improper and third one strictly.
Okay, not exactly. So the second one is proper and the third one is improper. So if the numerator degree is either equal or less than the denominator, then it is proper, while in one of the cases strictly proper. But if the numerator degree is more, then there will be an issue and it is improper transfer function. So whether the integrator is a proper, strictly proper or improper?
Strictly proper.
Improper. And then the derivative?
Improper.
Improper. So improper transfer functions are practically not realizable. So they cannot be realized practically. Any improper function. So PID controller cannot be implemented practically because the derivative part KDS is improper and improper transfer functions cannot be implemented practically because they have infinite bandwidth. If you draw the Bode plot, it will keep on increasing. So the bandwidth is infinite and hence they cannot be implemented. But if we need to uh, use a PID controller, then how are we going to do? And again, this is ideal PID. So for this case, we use practical PID. So what is the difference? So in the practical PID case, everything remains same, Kp plus Ki by S. Only slight difference in the derivative, we have another term in the denominator. Okay, so now tell me which transfer function is what? This is strictly proper, right? Again, it is not changed. What about the derivative?
Proper.
Proper. So now it can be realized. So derivative has a very like small term in the denominator, and this tau d is very small. So tau d is much smaller than 1, as if its effect is not there on the performance of the system because it is very small. So the denominator is very small, but it is there only for practical implementation. Else KDS cannot be implemented. So tau d value is much smaller than 1. So tau ds is almost close to 0. So that the term will be close to KDS. But for practical implementing, there has to be a filter, low pass filter. So that's why the low pass filter is kept here, but it is at a very higher frequency, or the time tau d is small, much smaller. So that's why we always use practical PID controller. That's why we call it practical. Ideal is impractical. It cannot be implemented. So that's why we call it practical PID controller because it can be implemented practically. So is this clear why we use this transfer function? Why sir has used this PID transfer function?
Yes, sir. Sir, one doubt.
Yes.
Is it valid only in analog controller or in digital also we cannot realize this PID
Yes.
controller?
In digital, very good question. In digital, you can realize because in digital, if you see, everything can be implemented in terms of Z inverse blocks. So, like in analog, all those cannot be implemented, which are improper. Like improper transfer functions cannot be implemented. Similarly, in digital, you can implement everything in terms of delay. Like I have a signal say u of n, and I want to use u of n minus 1, which is 1 cycle delay. So then you can use a delay block called Z inverse to implement that. But whereas I give you a signal u of n, and then I ask you to give me u of n plus 1. Using u of n, you cannot give me u of n plus 1, which is ahead of time. So that cannot be implemented in digital. So if you write the expression of PID controller, it can be implemented using Z inverse blocks. So now what happens? You can implement the digital PID controller. But in the case of analog, this issue is there. So sir has another course which is called Digital Control and FPGA-based prototyping in switch mode power converters, where he has discussed about the digital PID controller. So you can go through that course. I also have conducted problem solving sessions on that course as well. So you can go to my YouTube channel, and in the playlist, it will be at the top, so you can refer. It is digital control and FPGA based prototyping in switch mode power converters. So that is the updated, like the next part of this course. So this is like a prerequisite for that course, where in that course only the digital control is discussed. Here only the analog control is discussed.
Okay, sir.
So now if we further simplify this, we can get as G PID of S equal to KPS into tau ds plus 1 plus KI into tau ds plus 1 plus KDS square by S equal tau ds plus 1. Clear? So I will segregate all the terms, S square, S and constant. So S square, if I take, it will be KP into tau d plus KD. If I take S, it will be KI into tau d plus KPS, and then constant will be KI by S into tau ds plus 1. So I'll just further simplify. So GPID of S is, I will take KI common. Then I can write it as 1 plus K1S plus K2S square by S into tau ds plus 1. So now I am writing, first of all, this is the expression. So this is the practical PID. So now we are getting what is K1? K1 is nothing but the coefficient of S divided by tau Ki. So it is tau d plus Kp. Sorry, here there will not be S, it is just Kp. So Kp by Ki. And then K2 is Kp tau d plus Kd by Ki. Just understand the math. What I have done is I have considered this expression and I have expanded, like I have taken the denominator common and then rewritten the numerator in such a way that I have segregated S square, S and constant term. Now I have divided the numerator by Ki and then I have taken it outside. So the S square coefficient will be Kp tau d plus Kd by Ki, which I am considering it as K2. And then this term will be Ki into tau d plus Kp by Ki. So it is tau d plus Kp by Ki, which I am representing as K1. And this will become 1. So this is my overall practical PID transfer function. Is this clear?
Yes, sir.
Everyone?
Yes, sir.
So now we are going to use this knowledge about the practical PID controller that we have discussed. Because first of all, there is no question about implementing this because it is not practically implementable. So we are not going to discuss about this. We are going to discuss about designing the GPID of S for a buck converter, practical buck converter or ideal buck converter, and what are we going to follow to design the controller. So now this will take us to the next part, which is the PID controller in buck converter using pole zero cancellation. So whenever I'm saying PID, it is practical PID. So it is implied. So now we are going to discuss about the PID tuning. Yeah. Voltage mode control, buck converter. So for the simplicity, I'm considering an ideal buck converter. So now let me draw the block diagram again quickly. So we have the controller, we have the modulator gain, we have the duty to control to output transfer function, and then we have out V naught, and then I am not considering any gain. So this will be my V reference cutoff, and you should be comfortable with the block diagrams because they are very much needed. GVD and then V naught cutoff, and then this will be VRR cutoff. This is plus, this is minus. If a formula, this will be K of us. Okay. So for the time being, I am considering ideal buck converter. So if I write the expression, I'll get K loop of S is equal to GC into FM into GVT. So now, what is GC? GC is nothing but the GPID, right? So now let us write the expressions, all the expressions. So K loop of S equal to FM, I'll take it outside. What is my GC? GC is GPID, so I'll write this expression. So FM into Ki into 1 plus K1S plus K2S square by S into tau dx plus 1. Okay, so this is my GC of S. And anyone, what is GVD of S for an ideal buck converter?
V in
Okay, V
divided by
divided by 1 plus
1 plus S into L by R
S into L
plus
by
S square plus S square into LC.
R. Yeah, good. So also I'll want to give you one research paper of Professor Santanu Kabat, which is this. I'll maybe provide you the link. So in this, what happens is if you scroll down to uh, page number 14. So here sir has given different transfer functions of buck boost as well as practical buck and practical boost. So now we are in ideal buck converter. So this is the ideal buck converter and this is GVD. So you can get the expression. So it is easy just to look at it rather than going through all the you know videos and finding the proper transfer function, because this is in a given tabular form. You can directly get it. So if you see practical buck, here they have VE, omega Z, Q omega naught, and omega naught square. What are the expressions? If you just scroll up, in this table, sir has given the expression for ideal buck, practical buck, and everything. So this will be very helpful and handy in these two pages, just these two tables. Ignore about the rest of the paper. So in this, from these two tables, it will become very easy for you to get all the transfer functions. So if you need the link, I can provide you. So this is an open access paper, so you should be able to download. I'm giving you the link. So you should be able to download, just let me know. So in this paper from page 13, so page 13, one table, and page 14, another table. From these tables, you can get the expression. So it will become easy for you to have all the transfer function at a single place. Are you able to access it? Can anyone please confirm? Yes. Okay. Okay. Thank you. So this is the oral transfer function, K-loop transfer function that we have obtained. So now, when we do pole zero cancellation, what are we basically going to do is, we are going to cancel the two poles of the denominator with the two zeros of the controller. So basically what we are trying to do, so this and this will get cancelled, which means we'll get a few equations. One is K1 equal to L by R semicolon K2 equal to LC. We are cancelling it, so that's why it is called pole zero cancellation, and it is called stable pole zero cancellation because you cannot cancel RHP zero with RHP pole because RHP pole is not stable. So here the zeros are all on the left hand side as well as the poles, so all are stable. So that's why it is called stable pole zero cancellation. Stable pole zero cancellation. Okay, so once we do this, so what is left? We have K loop of S equal to Fm Ki into V in by S into tau ds plus 1. So, first of all, how many unknowns are there? Can anyone tell me what are the unknowns and how many unknowns are there? Like we are going to design a controller. So what are the unknowns that we are actually going to design in the process? Like what are we trying to find?
KP, KA, KD, and
AI.
KP, K, KD, right? Right? KP, K, KD, right? So tau d can be much smaller than 1, and it's a like just for practical implementation. So we are not going to design it through pole zero cancellation. You can put some very small value just for the practical implementation. So you can keep it at very high frequency. So the three unknowns are KP, KI, and KD. So let me write it here. So we have three unknowns. So how many unknowns are there? So we have three, which are KP, KL, KD. So in order to solve this, we need to have how many equations? So how many equations do we need to solve and obtain the values of KP, KA, KD?
3 equations.
Three equations. Until now, how many did we get?
Two equations.
Two equations. So we need another equation.
Two
So
equations.
yes. So we need another equation which we can obtain from a bandwidth. So say the bandwidth that we are targeting is omega c. So that means the magnitude of K loop of S at omega equal to omega c should be equal to 1 because at bandwidth the magnitude is 1. So 20 log of magnitude will become 0. So it will cross the that gain plot. So that's why it is also called as bandwidth or gain crossover frequency. So the magnitude should become 1. Agree? So this is our requirement. It is given in the question. Is this equation clear? How we are getting?
Sir, bandwidth and the gain crossover frequency are same, or there was something like 3 decibel drop from.
Yes. So yeah, so that's a very like good thing that you have pointed out, and also the misconception. So when we are talking about loop transfer function, so when we are talking about loop transfer function, so when we are talking about loop transfer function, so we basically consider 0 dB. And when we consider the closed loop transfer function, so loop transfer function means here K loop. And then we consider the overall closed loop transfer function. Then it will be giving minus 3 dB. So here this is K loop by 1 plus K loop. So how are we going to, like, the question is how 0 dB is related to minus 3 dB. So in this case, the magnitude of K loop is 1. That's what we are saying. So if the magnitude is 1, then 20 log 1 is 0. So if K loop is 1, K loop by 1 plus K loop is how much? Half, right? Around closely. Say magnitude is 1 and there is no imaginary part. So K loop by 1 plus K loop is half, right?
Yes,
Hello.
sir. Yes.
Yeah. So now if you calculate the dB, it will be 20 log half. So this will become minus 3 dB. So if we are going with the loop transfer function, which is K loop, then we have to consider 0 dB. But if you are considering the overall closed loop transfer function, which is V naught part up by V reference part up, then the entire system, if you draw the band Bode plot, then you have to consider minus 3 dB, which is the bandwidth. So both are same, but here it is 0 dB, here it is minus 3 dB, and it is coming because of this. So whenever you are considering K loop, it means the magnitude is 1, or in dB, it is 0. Is that clear?
Yes, sir. Clear.
So there is less than a minute. So if this meeting ends, kindly join that. So now if we calculate the value, we will get Fm into Ki into V in by omega into omega tau d plus 1 equal to 1. Sorry. Omega into square root of 1 plus omega tau d whole square. So we have considered that tau d is much less than 1. So we can consider approximation omega t tau d is close to 0 because omega tau d whole square, right? So if we consider this, then we'll get another equation. So if we calculate, then we can get Ki equal to omega, which is omega c by Fm into Ki. So Fm into V. So this is our third equation. Agree? So we got 3 equations, and we need to solve these 3 equations to get the 3 unknowns Kp, Ka, and Kd. Is this clear?
Yes, sir.
Yes, sir.
Now, if we also calculate the phase margin, so now in this process, we don't have any control over phase margin because we have already gotten the gains. So now if you calculate the phase margin, which is 180 degrees plus this phase, so we'll get phase margin is equal to 180 degrees plus the phase of this is minus 90 degrees contributed by S. And then the angle contributed by this is tan inverse tau d. So minus 90 degrees minus tan inverse tau d. Because we have considered tau d is much smaller than 1, this can be considered to be close to 0. So my phase margin is 90 degrees. So in this pole zero cancellation of a practical PID, this is fixed and this is fixed. And it cannot be changed. So what we have done is we have considered an ideal buck converter, which is under voltage mode control, and we are designing a practical PID controller. So we first got the K-loop transfer function. We have cancelled the 2 zeros of the controller with the 2 poles of the plant. From there, we got 2 equations. After simplifying, we were given with a requirement of bandwidth omega c. So using that, we have obtained third equation for Ki. And then using this, we have calculated phase margin, which is 90 degrees, which is fixed and we don't have any control over it. So we got 3 equations. From there, we can calculate 3 unknowns, which are Kp, Ka, and Kd. Is this clear?
Yes, sir.
So if you have any doubts, you can ask, else we'll solve one problem quickly. Okay. If you don't have any questions, then let us solve this problem quickly. So let me read out the question. Consider an ideal buck converter with the following specifications, where Vin is 16 volt, V naught is 1.5 volt, inductance is 180 nanohenry, capacitance is 1 millifarad, resistance is 0.05, switching frequency is 1 megahertz. Calculate the steady state duty ratio and write the control to output transfer function. And if Vm is 1 volt, what will be the control voltage at steady state? Design a practical PID controller using pole zero cancellation. So let us go step by step. Can you calculate the steady state duty ratio? How to calculate?
V out by V.
So how much is the value? So under voltage.
1.5 by 16 equal to 0.094.
0.094. So duty ratio is 1.5 by 16, which is 0.094. Okay. Everyone is able to get the same answer? Others?
Yes, sir.
So write the control to output transfer function. So now, as we have already written that, I'll just copy it. You just tell me the transfer function, calculate it with the values given, and let me know. So B by 1 plus SL by R plus S square S. We'll rewrite it. So GVD equal to V by 1 SL by R square S. So can anyone calculate and let me know what is the value that you are getting? So these are the values, and this is the expression. Has anyone calculated?
16 divided by
16 divided by
1 plus 3.6 into 10 power minus 6 s.
just 16 divided by 1 plus
3.6 into 10 power minus 6 s
okay
plus 1.8 into 10 power minus 10 s square.
So let me wait and check if others are also getting the same answer. Can anyone confirm if your answer is matching to this?
Yes, sir, same answer.
Same answer. And now what will be the answer for C? Part C.
Duty ratio equal to V con by V reference.
Duty ratio equal to. So what I'm asking is control voltage, right? So what is the relationship between control voltage and VM for voltage mode control? If we go back, today I have discussed, right? Here,
V con by Vm equal to
duty ratio, right?
D.
So V con by VM equal to duty ratio. Yes. So for this is for voltage mode control, of course. So V con by VM equal to duty ratio. So now what is V con? V con at steady state. What is V con?
Same as duty ratio.
Same as D. Yes, yes. I was writing 0.094, same as D, because VM is 1. Now you see how control voltage will change, right? So if my VM is 2, then Vcon will be into 2. If my VM is 3, then Vcon will be into 3. So accordingly, my control voltage will change. So the controller will update its value so that I'll get the same output voltage. So in that way, output voltage is regulated. So now I have asked you to design a practical PID controller using pole zero cancellation. So uh, is any data missing, or whether uh, whatever is given in the question we can proceed with? So I have asked you to design a practical PID controller, and I have given you these uh, values. So if I want to proceed with this, something is missing, or can I solve it? Like, because in the previous slide,
Gain crossover frequency.
yes, yes. So gain crossover frequency needs to be given so that we will get the third equation. So I'm considering gain cross FC is FHW by 10, 1/10 of the switching frequency, which also means omega C is 2 pi FHW by 10. So this is the third requirement. So now, because we have already derived, let us not waste time in deriving. I'll just copy paste the equations. So we'll do step by step. Let us put the equations that we have. Okay. So these are the three equations so that we'll get three unknowns, K1, K2, Ki. So what is my transfer function? So this is my overall transfer function, GPID. So kindly solve the question and let me know what are the gains K1, K2 and Ki that you are getting. So tau d is something very small. So because the time period is 1 microsecond, I can consider tau d to be say 1 microsecond or 0.1 microsecond. I just want it to be very small. So maybe I can consider tau d to be t by 10. So 0.1 microsecond. So this is not coming from the design. Basically, this is coming from the practical implementation of PID controller. So we'll try to keep it as small as possible. So it is not a design problem. This is just an implementation issue. Okay, so if you have not noted down, I will zoom out so that you can get all the. So please note down the values and then calculate the gains one by one. Then we can cross it.
Sir, K1 is 36 into 10 power minus 7.
Sorry, K1 is
36 into 10 power minus 7.
36 into 10 to the power minus 7.
Yes, sir.
K2
K2 is
1.8
18.
into 10 power.
into 10 to the power
1.8 into 10 power minus 10.
10. Okay.
Yes,
Ki
same. 39.269 into 10 power 3.
So is this what everyone is getting? So now from this you can also write the overall transfer function. And then if you want to divide by s, you can also divide by s. So let us not like write in practical PID, let us write in transfer function so that it makes things look simpler. So we have GPID of s equal to Ki, which is 39.269 into 10 to the power 3 into 1 plus K1 is 36 into 10 to the power minus 7 into s plus K2 is 1.8 into 10 to the power minus 10 s by s into tau d I am considering 0.1 micro. So it is 10 to the power minus 7 into s plus 1. So I'm considering as small as possible. So this is the overall PID transfer function, practical PID that we have obtained for an ideal buck converter with these specifications operating under voltage mode control. So the entire process is clear how we are getting.
Sir,
Any
what is the
doubts?
value of frequency?
What is the value of
Yes. In the question, what is FSM, FSW?
FSW is 1 megahertz. So 10 to the power 6. So time period is 1 micro, 10 to the power minus 6. And I have considered tau d to be t by 10. which is 0.1 micro, so 10 to the power minus 7. So tau d is not coming from any design as such. Like we are using it so that the controller is implementable. So we try to keep tau d as small as possible. Typically, people consider fraction of time period. So I'm considering 1/10 of the time. So 0.1 micros, 10 to the power minus 1. So this is not there in the design at all. We have ignored for the simplicity of design, but then we have added this value so that it is practically implementable. So now this becomes a proper transfer function. If this is not there, then it will become improper transfer function. Clear?
Yes, sir.
So if you don't have any doubts, then we'll move to another important topic, which is type 3 design of voltage mob or any type 3 compensator. So can anyone tell me why type 3 compensator is needed?
Here phase margin was not controllable.
Yes, very good. So in the previous case, where you have considered a practical PID with pole zero cancellation. So practical PID stable pole zero cancellation. So in this case, phase margin is 90 degrees and not controllable. So we need it to be controllable. So we have more flexibility. We want to control or have a control over both bandwidth as well as phase margin. So now let us directly not go to type 3 compensator, but let us see how we are getting the requirement of type 3 compensator. So now I want to consider a practical PID. So let us consider sorry, not practical PID, practical buck. Practical buck converter. Okay. So I'll take the transfer function from the paper that I have shown previously. So mine is practical buck converter. Practical buck converter GVD is VE into 1 plus S by omega Z. Here this is omega ESR, and the denominator we have 1 plus S by Q omega naught S square by omega naught square. VE is nothing but VE. So VE in practical buck is V in by alpha. And alpha is what? Alpha is R plus RE by R. So these are all the expressions, and sir has generalized so that it will make our life simpler, and we can just have a look at this table and get all the transfer functions. So now I'm going to write the practical buck converter transfer function, which is GVD of S equal to VE, which was V in by alpha, into 1 plus S by omega ESR by 1 plus S by Q omega naught plus S square by omega naught square, right? So this is the control to output transfer function of a practical buck converter. So now what are the requirements that we need to have in the controller? First of all, we need two poles to cancel, sorry, two zeros. We need two zeros to cancel the two poles of the plant, which are this. So in order to cancel these two, we need two zeros in the controller, which we already had in the PID controller. If you see, we had this in the PID controller. So this is cancelling with this. Now what else needs to be cancelled? the ESR, for cancelling ESR, we need one pole, right? So we need one pole. Cancel the ESR 0. And we need one pole at the origin. Which acts like an integrator for steady state error. Zero steady state error. Okay. Now, if you see two zeros, two poles. With this, what we have done, we have cancelled the ESR. Okay. And then we also have cancelled both the zeros. And the controller will have a DC gain. It will have a DC gain. So that bandwidth can be selected. So now the controller needs to have two zeros, one pole and another pole at origin and also a DC gain so that both the poles of the plant along with the ESR 0 can be cancelled and we'll have an integrator for zero steady state error and bandwidth can be selected. But in addition to that, now we need one additional pole so that we'll have the freedom to select phase margin. So now if we summarize the requirements of the controller that we have two zeros. Anyway, DC gain is there, so DC gain is there. And then we have two zeros. And then we have three poles, one at origin. So these are the requirements that we have obtained. Now if we write the transfer function of the controller GC of S, we will get GC of S equal to its gains here, let us say KC. So KC into two zeros, right? 1 by S by omega Z1, 1 plus S by omega Z2 divided by integrator and the other two poles, 1 by S omega P1, 1 plus S by omega P2. So this is the requirement of the controller that we have obtained, and this is a type 3 compensator. So now we understand why do we need a type 3 compensator, because we have not just randomly chosen type 3 compensator, but based on our requirements of the number of poles and zeros that the controller needs to have so that the poles and zeros of the plant can be cancelled. Based on this, we got this. Is that clear?
Yes, sir.
Everyone?
Sir.
Okay. So now let us do what we have done in the previous case. Let us cancel everything and then let us get the expression so that we'll get two equations, two unknowns, and then based on that, we can solve those two unknowns. And then we'll have to choose bandwidth, we have to choose phase margin, and then we'll get the equations. Once we get the equations, then we can derive the gains, and then we'll solve one problem based on them. So first of all, let me copy paste this and let me write side by side. So this is my plant transfer function, and this is control transformation. Control. Okay. So now let me change the colors so that we'll know what is getting cancelled with what. So omega ESR, say it is getting cancelled with the whole one. So these two are cancelled, and the denominator is say cancelling with the numerator. So instead of writing it in terms of two poles, what I will do is I will write in this term 1 plus K1S plus K2S. So is this clear? So now you know which is getting cancelled with what. Clear?
Yes, sir.
So in the previous PID case, practical PID, we had three equations to solve for three unknowns. So now in this case, how many unknowns are there and how many equations do we need?
KC, K1, K2.
Yes. That's it, or any other unknowns are there?
Omega P2.
Okay. So total how many equations are needed and how many unknowns are there?
4 unknowns and 4 equations.
4 or 5 unknowns?
Omega P1 we can take as omega ESR.
But still that is also an unknown, right? So that is the equation we are getting. Omega P1 equal to omega ESR is an equation that we are getting. So overall, how many unknowns we need to find? Here, how many unknowns are there?
So 5.
5 unknowns. So we need to get 5 equations. So let me write. So we have 5 equations, 5 unknowns. So we need 5 equations. So till now, how many equations we got? We got omega P1 equal to omega ESR. And then we got K1 equal to 1 by Q omega naught. And then we got K2 equal to 1 by omega naught square, right? So we got already 3 equations. So how many more we need?
2.
2. So from where we are going to get the 2 equations? So if we look at the requirement, so from where can we get the 2 equations?
Bandwidth.
Bandwidth, one equation, and other equation.
Phase angle, phase margin.
Phase margin, yes, very good. So now we'll get another 2 equations, one from bandwidth, one from phase margin. So let us write the loop transfer function. So in the loop transfer function, we will have GVD into GC into FM. And in this, omega ESR and omega P1 gets cancelled. The denominator will get cancelled with the numerator. So whatever we are left with, I am writing the expression. So we have K loop of S equal to, in GC, we are left with V in by alpha and one FM is there. So V in into FM by alpha multiplied by, here we have Kc by S into 1 plus S by omega P2. So Kc by S into 1 plus S by omega P2. Is this clear? So this is the overall loop transfer function. From here, we are supposed to calculate the bandwidth as well as phase margin. So we know the requirements are already given. Which are omega C and phase margin, both are given. So how are we going to calculate omega C? We know that the magnitude of K loop of S at that particular value is 1, right? So we will get V in Fn Kc by alpha into 1 by omega c into square root of 1 plus omega by omega p2 whole square equal to 1. Agree? This is the equation omega c. Or any confusion is there? Basically, I have calculated the magnitude of this at omega c. So basically, what does this mean? This means K loop of S magnitude at omega equal to omega c is equal to 1. So I'll replace S by j omega and calculate the magnitude. S is j omega c, magnitude is omega c. This is 1 plus j omega c by omega p2, which is square root of 1 plus omega c by omega p2 whole square. Clear?
Sir, this Kc, is it same as that Ki in the initial?
No. Here there is no Ki. This is a different type 3 compensator. So, like if you see here, we got some Kc
Okay,
gain,
okay.
and then in the PID, from this, if you like simplify it, and then we have taken Ki common, and then we got this expression. So if you add another pole
Okay.
here, then it will become type 3 compensator. But this Ki from the PID need not be the same as Kc in the type 3. Maybe same,
Okay,
may
sir,
not be
understood.
same, but I'm using two different terminologies so that things will be different. So if we calculate Kc from here, we will get Kc equal to alpha omega c by V in into Fn into square root of 1 plus omega c by omega p2 whole square. So this is another equation, which is the fourth equation that we are getting. That we are getting from this bandwidth. So now if we calculate phase margin, so phase margin is nothing but 180 degrees plus the angle of this at omega equal to omega c. So S will contribute to 90 degrees and this will contribute to tan inverse 1 by omega p2. So we'll get phase margin is equal to 180 degrees plus one is minus 90 degrees, another one is minus tan inverse 1 by omega p2. So from this we'll get another equation, which is phase margin equal to 90 degrees minus tan inverse omega p2, right? Sorry, omega c by omega p2. I made a mistake. So this is omega c by omega p2. I think in that case, previously also maybe I have made a mistake somewhere. This will be tan inverse omega c tau d. So just a moment. So anyways, we have neglected it to be 0, but the expression will be tan inverse because dimension should be same. Omega c tau d will not have dimension. Tau d has a dimension. Okay, it's okay. So this will be tan inverse omega c by omega p2. Phase margin is given, omega c is given. So you can calculate omega p2. Once you calculate omega p2, you can substitute in this expression. You can get Kc. Once you get Kc, you already have K1, K2, omega p1 calculated. So we can calculate the entire GC transfer function, which is the type 3 compensator. So maybe I'll quickly summarize before we solve one problem. So we have started with why do we need a type 3 compensator? We have understood that the practical PID controller with stable pole zero cancellation, the phase margin is 90 degrees and it is not controllable. So we need additional degrees of freedom. So we have considered a practical PID controller and we have seen what are the requirements of a controller. So in order to cancel the two poles of the plant, we needed two zeros. In order to cancel the ESR zero, we needed one pole. And we needed one pole at the outset for the integrator so that the steady state error will become zero. And then we needed DC gate so that the bandwidth can be adjusted. We needed an additional pole so that the phase margin can be adjusted. So based on all this, we needed one DC gate, two zeros, three poles, one at origin. So this is the overall transfer function of the controller, which resembles that of a type 3 compensator. So basically we need type 3 compensator. So now we needed five unknowns. So we need five equations. So if you cancel the do the pole zero cancellation, we'll get three equations. So after that, this is the loop transfer function. So from here, we'll need two more equations. One is coming from the bandwidth, which is this equation. Another one is coming from the phase margin, which is this equations. So overall, five equations, five unknowns, which we need to solve to get the controller gains. So I think the meeting will end within a minute. The time is less than a minute. Once this meeting ends, we'll solve one final problem for today's session. Before that, do you have any other queries, further queries? Any queries? Can you see my screen?
Yes, sir.
So any doubts before we start solving the problem? Okay. In case you do not have any queries, then we'll solve the problem. So consider a practical buck converter with the following specifications. Vin is 16, V naught is same, inductance, capacitance, everything is same. R is 0.05, switching frequency is 1 megahertz. R on is 2 milliohm, RL is 0.5 milliohm, and RC is 1 milliohm. So now I'm asking, write the control to output transfer function and find the pole locations. I think this is redundant because if you write that, then we can get the pole location. So now design a type 3 compensator targeting a bandwidth of FSW by 10 and a phase margin of 45 degrees. Is the question clear?
Yes, sir.
So let us start with the transfer function. So this is the overall transfer function. And yeah. So let us write one by one terms. So alpha is R plus RE by R. And RE is R on plus RL. So we have alpha equal to R plus RE, right? R plus RE by R, where RE is RL plus R on. Okay, and omega ESR, which is practical buck 1 by R plus RC into C, right? Yes, practical buck 1 plus ESR 0, R plus RC into C. So omega ESR is 1 by R plus RC into C. And then we need to find Q, and then we need to find omega naught. Q is alpha into RC plus RE by ZC plus ZC by R inverse. So alpha into RC plus RE by ZC plus ZC by R whole inverse. And ZC is nothing but square root of L by C. So this is a very lengthy problem, but it's very simple. All we need to do is first calculate one by one, and then we have already derived the expression for gain, so it becomes simpler. Only we should not make any calculation mistake, else it is simple. Then we need to have the expression for omega naught. So omega naught is square root of R plus RE by R plus RC into 1 by root LC. So omega naught is square root of R plus RE by R plus RC into 1 by square root of LC. So is this clear until this point? So we need to first find the transfer function, but before that we need to find all these things one by one.
Sir, where that omega is, sir, where it is given in that paper? Can
Okay,
you show it
so
once?
yes. So this, if you go here in the practical buck converter, which is the third row, we have omega z here. In this expression, there is omega z2 also. So there are omega z and omega z2. So if you come back here, there is omega z here and omega z2. Oh, sorry, I think this one by bit. It is 1 by RC into C. Sorry, this is not this. Okay, that's a different one. Omega RC into C. ESR0, sorry. This is for a different one, I think. So omega z1 is different, omega z2 is different, omega z is different. We needed omega z. So omega z is 1 by RC into C for a practical buck converter. And here RHP0 is not applicable. And this is omega z1, this is omega z. Clear?
Sir, in the lectures, somewhere that alpha equal to R by R plus RC was shown. Is it for boost or
Alpha is
R by R plus RC?
R by R plus RC. I think that may be a different alpha. So actually, sir has used two different alphas. So that alpha sir has used in the matrices, ABC matrices. So yeah, I think
Okay.
it is not a great idea to use two alphas, else it will be confusing. So here, maybe let us not consider this as alpha. Let us consider this as alpha dash. So that alpha sir is considered in the modeling where you will get R by R plus RC. Yeah, that's a good thing that you have pointed out. So let us consider this as alpha dash. So that is different from this. Clear?
And here the RE will be RL plus
RL
R1.
plus R1. So kindly
Okay.
do one thing. Let us kindly write down all the values of this so that I can scroll down and then we can quickly solve the problem. So write down all the values of V in V naught. And once you are done, let me know. Then we'll start solving one by one. So we have to calculate all the values and then we'll start getting the gain. So it will also be like a practice so that we'll not make mistakes. Once you note down the values, let me know.
Okay, sir.
So can you calculate alpha dash? So let us start calculating one by one. So what is alpha dash? R plus RE by R. Or tell me what is RE? What is RE?
2.5 million.
2.5.
2.5 million. Very good. So it is 2.5 million. Now what is alpha dash? R is 0.05. So use a calculator if you have. I think I won't have currently with me. So you calculate and just write down the value. Alpha dash will be slightly more than 1. So it will be 1 plus RE by R. So 1 plus 2.5 by, this is how much? 50 milli. So 25 by 500, 1 by 20. So I think 0.05, 1.05, right? Something like that. Is it 1.05?
Yes, sir,
Alpha dash.
1.05.
1.05. Okay. And omega is, sir? One by RC into C. C is 1 milli. RC is also 1 milli.
1 into 10 power 6.
Yes. 10 to the power 6. ZC. Square root of L by C. L is I think 180 nano. By C is 1000. Nano. 10 to the power 6 nano. Okay. ZC.
0.013.
0.1. Parvati, you're also solving, right?
Yes, sir.
Okay. Are the values matching with yours?
Yes, sir.
Okay. Now let us solve for Q and then we can calculate omega naught. So tell me the value of Q and then omega naught. So I don't have calculator, so you please calculate and let me know. Omega naught will be close to 1 by root LC. Q, please calculate. Q, there is inverse here, so don't make that mistake. And this is RC plus RE.
Sir, I got 1.984 as Q.
1.984. Okay. Parvati, please confirm whether you got the same value or not. So calculate omega naught.
Sir, Q, the equation has a inverse, right? One.
Yes, yes, there is an inverse. Is your answer not matching? See. Let me also calculate. RC plus RE is how much? 3.5. This point. 1.984, right? I think I'm also getting 1.984. Omega naught, how much are you getting? I'm getting 75,000. Yeah, 70.
75.623 into 10 power 3.
Even I'm getting the same. Parvati, are you able to get the values, similar values?
Doing
Okay. Okay, we'll wait for you. Once you are done, let us know, then we'll start. So this is the overall transfer function that we have obtained. We just have to plug in the values. I have just written it like this. So this is part A. Once you are done, we'll start solving part B.
Yes, sir.
Okay, you're also getting it. So now we got the transfer function, and then the requirement is given as bandwidth is 1/10 of the switching frequency, phase margin is 45 degrees. So what we are supposed to do is we want to calculate all the gains. So let us copy paste all the 5 equations. Or first we'll calculate these 3 and then we'll calculate the other 2. So now what? Now tell me what is omega p1?
Omega is 10 power 6.
And k1 and k2?
K1 is
K1
6.66.
0.66 into
10 power minus 6.
Is this what everyone is getting?
Yes, sir.
Okay. Calculate K2.
K2 is 1.748.
1.748 into
10 power
Minus 10.
minus 10. Okay. Okay. Now we got 3 unknowns. We need to get the other 2 unknowns. So first, as discussed, first we need to solve for this. Once this is solved, and I can solve this. And what are the requirements? The requirements that are given is phase margin equal to 45 degrees, and omega c is 2 pi FHW by 10, where FHW is 1 megahertz. So now, can you calculate first what is omega p2, and then we can calculate kc. So first calculate omega p2, and again this is alpha dash I discussed. So first calculate omega p2, then we can substitute it again.
So omega P2 equal to omega C.
Yes, very good. So omega P2 you will get as
Yes, sir.
omega C. So can you calculate the value and let me know?
2 pi into 10 power 5.
Yes, yes. Tell the value in like normal decimal.
Uh, 6.28 into 10 power 5.
Okay. So now we need to calculate Kc. So omega C by omega P2 is 1. So this will become square root of 2. And Fm is not given. So you can consider Vm to be 1 volt. So that will be there. So we'll get alpha dash omega C into root 2 by Vm. So can you calculate Kc?
.31 into 10 power 3.
0.21 into 10 to the power 3. Are you getting the same answer? Can you cross?
I am doing, sir.
Okay, okay. Did you get the same case?
Yes, sir. 58.28.
Okay, into 10 to the power 3. Okay, so now if you write the overall type 3 compensator, it is Kc multiplied by 1 plus K1s plus K2s square. So let me write it. So Gc of s is equal to Kc, which is 58.31 into 10 to the power 3 multiplied by 1 plus K1 into s, which is 6.66 into 10 to the power minus 6. 6.66 into 10 to the power minus 6 into s plus s square coefficient is 1.748 10 to the power minus 10 s square divided by 1 plus s by omega p1 10 to the power 6 1 plus s by omega p1 and 1 plus s by omega p2 is 6.08 10 to the power 5. So this is the overall PID controller that we have obtained. So if you see, the overall idea is simple. What we are trying to do is we are basically cancelling some holes with the zeros to calculate the controller gain. So we need to know which are getting cancelled with what, and then we'll have bandwidth and phase margin. So the number of equations are 5, the number of unknowns are 5. So first we have to step by step calculate the plan transfer function. From there we'll get the unknowns. So looking at this uh, might make you feel that this is very difficult, but if you see, things are very simple. Once you write down all the steps, then and solve one by one variable, like results are already there. Only you have to calculate it and make no mistakes. Then you will get the answer. So do you have any doubts? If you have any queries, you can ask. I'll summarize today's session. In case you don't have any doubts, I'll just quickly summarize what we have discussed today. So in today's week, it's all about small signal design as well as controller tuning for voltage mode control converter. And I have discussed buck converter, and Kelvin might have discussed boost converter, I guess. So we have started with the small signal closed loop block diagram where we have considered voltage mode control and we have drawn the overall small signal block diagram, and we have also seen what is the K loop expression. So we have seen that the requirements are bandwidth and phase margin, and meeting those requirements, the objective is to design the controller. So we have started with PID controller, and we have understood why ideal PID controller cannot be implemented practically because of the improper transfer function of the derivative. And because of this, we need to go for a practical implementation. So we will add one low pass filter in the derivative, and that's why we call it as practical PID controller, as it is or it can be implemented practically. So now the transfer function is having an integrator which is strictly proper, and the derivative which is proper, and the overall GPID of S is proper. And we have rewritten this expression in this expression where we have GPID of S is Ki into 1 plus K1S plus K2S square by S into tau ds plus 1. So now using this, we have considered an ideal buck converter operating under voltage mode control, and then using the stable pole zero cancellation, we have designed the controller. We have seen there are three unknowns, Kp, Ka, Kd, and then we needed three equations. So first we have cancelled the poles of the plant with the zeros of the controller. We got two equations, and from the remaining equation, we had only one unknown. So we can only select either bandwidth or phase margin. So we have selected the bandwidth, and from that we have gotten the third equation. So now the phase margin is fixed to 90 degrees, and we don't have any control over them. So we have only three equations, and we got three unknowns, and phase margin is fixed. Kindly note that the tau d is not coming from the design, but from the practical implementation issue. So tau d can be made smaller. So here I have considered tau d to be 1/10 of the switching time period. So unless anything is mentioned, you are free to choose a fraction of time period. So we have solved one more problem, the first problem of today's session, where an ideal buck converter under voltage mode control is considered, and we have calculated the steady state duty ratio as well as the control to output transfer function, and then the control voltage. Now, using the results that we have obtained in the previous page, we calculated the unknowns in the controller. We got the three unknowns, and then we have rewritten the control transfer function as this. So this is the overall practical PID controller for this ideal buck converter operating under voltage mode control. But we have seen there is a limitation, which is the phase margin, which is fixed to 90 degrees and cannot be controlled. So in order to have that additional degree of freedom, we might have to consider one additional pole to select the phase margin as well as bandwidth independently. So here we have considered a practical buck converter. So based on this, our controller needs to have two zeros to cancel the two poles of the plant, and one pole to cancel the omega ESR or the zero of the plant, and one pole at origin for zero steady state error, and one additional pole to have freedom to tune the phase margin as well as the DC gain so that the bandwidth can be tuned. So now based on all this, we need one DC gain, two zeros as well as three poles in which one is at origin. So now the requirement says that we need a type 3 compensator. So now in order to design the type 3 compensator, we have written the control to output transfer function of a buck converter next to the controller transfer function, which is the type 3 compensator, and we have seen which are getting cancelled with what. So after pole zero cancellation, we got three equations. Now if we write the loop transfer function, we need two more equations. One is coming from the bandwidth, another one is coming from the phase mapping. So first we solve one equation and then substitute that in the other equation to solve for both the unknowns, omega p2 as well as kc. So in order to get an overall idea, we have considered a practical buck converter operating under voltage flow control. So first we have to get the control to output transfer function. So we have written the control to output transfer function and the expression for all the unknown variables, and we have solved one by one without making any mistakes. Once we got the control to output transfer function, using the results that we have previously derived, we got the unknowns, which are omega p1 as well as k1 and k2, which is very straightforward. After that, the other two equations are coming from the bandwidth as well as phase margin. because phase margin is given as 45 degrees, we got one equation which is omega P2 equal to omega C, and then we got the fourth unknown which is omega P2. Now using this, we have substituted in this final equation to get the unknown, final unknown Kc. Once we got all the unknowns, we have written the overall type 3 compensator equation, and all the unknowns are obtained from the equation. So 5 equations, 5 unknowns, all are solved, and this is the overall compensator. So this summarizes today's session, week 7. If you have any queries, you can ask. Else we'll again meet in the next week, and I'll be taking as usually on Monday, and Kelvin will be taking on Tuesday. Today he had some other work, so that's why he could not conduct it today, and we have exchanged. So any queries you have? Okay. If you don't have any queries, then I'll end this session here. I wish you all the best for week 7. It is simple. So refer to that paper so that you will get all the transfer function at a place. While solving the assignment, also you can keep this paper next to you so that you will get the transfer function with all the terms. So follow the same step-by-step guidelines that I have mentioned. First, calculate the transfer function. Don't think about the controller. Once you get all the terms in the transfer function, then using pole zero cancellation, you will get one by one term in the controller. So you have to see how many unknowns are there and how many equations you will get. So from pole zero cancellation, you will get few equations, and the rest of the unknowns will come from the equations from the bandwidth as well as phase margin. In the case of practical PID, phase margin equation is not there because we don't have control over it. Whereas in the case of type 3, you will have the control over phase margin, so you are getting that additional equation. So this is the overall idea. Basically, number of equations, number of unknowns, but how we are getting it, that is the today's discussion. So with that, I'll finish week 7. If you want to discuss anything, you can ask.
Sir, can you show me that paper that you have shared?
Yes, yes. This one.
Sir,
Yeah. I have also shared the link in the chat box, so you can access it. It is open access, so you should be able to download.
okay, sir.
So maybe I can also attach the screenshot, so it will be there in the chat. I'm also attaching the screenshots in the chat, which you should be able to download. So anyways, you can go through the paper later also, up to you. But I have given paper link, which is also open access, and also the screenshots, so that keep them with you, and you can have an overall understanding of what is happening.
Thank you.
sir.
So I wish you all the best for week 7. See you again on next Monday. Good night.